This is the ELTE Week 5 or Module E lecture on timers, counters. Let's get it caught up here. The video lecture activities are, you're going to download the PowerPoint, obviously, and click the lecture video, which is this. You're going to follow the video and prompt it and stop when it asks you to stop and watch some other videos. You're going to fill out the video lecture worksheet, turn in a completed lecture worksheet. So here are our outcomes. How are RTO and TON timers similar, and how are they different? How do TOF timers work? What is meant by the term cascading timers? What are the benefits of using the latch and unlatch instructions for memory? Name 3 practical uses of PLC timers. What is the relationship between time base and total time of a timer? When is the .dn bit of a timer true? When is the .dn bit of a counter true? Let's start with a bit logic module D review. We learned about internal bits or binaries with the bit addresses of B3. So we had B300 all the way up to 15. And then the first number here can go all the way up to 255. Sorry, this should be /15, 255/15, which would be 4,096 total bits. Bits are not associated with a field device. They're just internal, which is saves us from consuming a connection point on an output card. Bits are typically used for logic, so anytime you have to replace a control relay and some logic, it's probably a good idea to use a bit because the PLC has replaced the control logic with bits. And bit status are shown in the data table. It's a great way to address, pull up the data table and just drag the bits in. And then you can also check the bits and see if they're high or low. So when should you use a bit for memory? Is the question. Once again, that bit should be used for memory when you're replacing a control relay, and we'll look at some options here in a minute. We looked at motor starting. Do not use a bit for motor starter memory. We're going to review the motor starting options, and that's what the lab taught us. We want to use the auxiliary contact for memory because the auxiliary contact is real, and so if the auxiliary contact drops out, the PLC senses that, whereas the bit is fictional. You use normally closed heater contact to the brake latch in the event of overheating. So if you wire that heater contact in the rung and that opens, that will break the memory. And once again, the heater contact is real. It's not fictional. So the PLC will be sensing that it actually has changed state. And we notice that you wire the e-stop normally closed and then use an XIC open contact in the ladder logic. Field devices can be wired into the input module as normally opened or closed. Certainly, a push button could be wired normally open or normally closed into the module. An auxiliary, there is open and closed auxiliary contacts on some starters. And the heaters can open or close contacts. Field devices are almost always programmed as normally open contacts. How come? Because if you program the field device as a normally open contact, then it behaves the way that it is wired into the module. I'll say it again. If you program your field devices with open contacts, then on the logic, it behaves the way that it is wired into the module. Here's the motor starting review that I talked about, so you want to watch this. And it talks about how we use the e-stops wired normally open or closed and the overloads and auxiliaries, and so understand that, and then the last statement will make more sense. We did some cross-reference. The program has cross-reference feature that lists the rung numbers of the coils and contacts, which is great for troubleshooting. The problem is that the rung references don't really indicate whether a contact is in series or parallel. So you can't really reverse engineer a program based on the cross-reference because it doesn't tell you if it's in series or parallel. In 131, every rung got a number. In PLC ladder here, the parallel rungs don't get their own rung number. So that's the problem there. We did an online edit. You can just double click the rung when you're online, and then you can make some changes, change instruction types, for example, and then you could test your edits, compile your edits, and then assemble them, and then you can just do it online without going online for quick edits. I don't mind doing some quick edits. If you're going to make substantial changes, you should probably do it offline. Because what's good or bad about this? Well, if you go online and you make a bunch of edits, then you have to upload that program back to your computer. Otherwise, those changes are only on the PLC. They're not on the offline program. So you get in trouble when the offline program, which a lot of times is the master program that somebody is counting on to be able to download that at any time if the RAM is lost. But if that's no longer matches the one that's in the processor, well, then it's going to erase it, and so any changes will be dismissed. So you got to keep track of your online edits. You got to upload and make notes of them and do revision levels. Otherwise, people are going to get confused about what's the most current program, the one that's in the processor or the one that's on the computer. We went over some rung comments. So here's an example of some rung comments. So typically, I don't put a rung comment here. It says part is sensed in stack feeder and cylinder extends feeding part. I typically don't put one on every rung. Essentially, these three rungs here are accomplishing this stack feeder here. Okay, and so I put a rung comment there to kind of group these three rungs together. Same here, part is transferred via conveyor to robot to pick up location. Maybe there's 3, 4, 5 rungs that accomplish that. That way I've just kind of organized sections of the program. Rung comments and also device comments are really important to have everything documented here. And then when you cross-reference to try and problem solve, you get a lot of information, and it helps with your troubleshooting. We did some solid-state ghost voltage. We hooked up the TRIAC module, and we just plugged the multimeter into it, and we got voltage, which obviously there was no voltage there because there wasn't a 1 in the data table, there wasn't a light on the output module, but the multimeter said that we had voltage. As soon as we put a load on there, the voltage went away. The load did not go on, so that was what we wanted to see. And the reason is when you use a high impedance meter, it kind of triggers that gate on that solid state switch, and it opens and you get a ghost voltage. The moral of the story is if you're not sure, check these with a load. You can get a small light or something like that, like what we did, and you can touch it, and it will, if it's truly got voltage there, it will come on. So you've turned in homework and quiz that has been reviewed. And so we'll move on to week 5 topics, which are latching and unlatching coils, timers, and counters. So latching contacts. We talked that output should only be addressed and used once. Otherwise, you don't know if it's on or off. It'll scan, and sometimes it'll be on, and sometimes it'll be off. It can be very confusing, but typically the last time it's used will be the state of it. So don't use it more than once, or you're going to be confused. Bit addresses are also typically only used once because the bit would be on or off. It's one part of the program says it's on, the other part of the program says it's off. Depending on where it's at in the program, you're going to get contradicting outputs of the bit, and you're going to be confused. A bit address can be assigned to an output latch, OTL latching coil, and a bit address can be assigned to an OTU unlatch. So could a light or any kind of an output. But what these are is these OTL and OTU, these simulate the latching relay that we learned about in 131. The OTE is just the output energize. These also go on to the coils in a program, but it's latch and unlatch. It says what's the best way to perform. I'm going to take a look at 3 different ways to accomplish this memory. 2 push buttons with the OTE, 2 push buttons with a bit, and 2 push buttons with using the new OTL and OTE. So we look at the first one here. Here is a latch, or a memory. Hit the start. Assuming that the stop is wired normally closed, then this open contact behaves the way that the field device is wired. That's what I was talking about. So if the stop is wired normally closed, this is true. So here we brought on a light. We used a contact associated with this output to close. So this would create memory. The only drawback is that if this was supposed to be logic instead of actually latching on a light, if we want, then we've consumed a terminal on the output strip. This contact here is totally fictional. It doesn't exist, and that's fine. The other way we did this was with a bit. So this is more like a control relay, because control relays no longer exist with a PLC. We're doing it with bits. So if the start-stop hit, we would energize a bit. The bit's fictional. It's internal to the PLC. This closes, and this also closes, which turns on the light. Okay, so this is a little bit cleaner because we've used a bit, and we can now use this bit later on in the program if we need to have it energized based on this top one here. And then the last one here shows the OTU and the unlatching and the latching situation here. So the way this works is if I hit the start button momentarily, just push it and let up on it, bit 30 latches on. And it will stay latched on because it's a latching bit. It'll put a 1 in there, and it'll stay a 1 in there until I get the unlatch. Now here's one of the cases where items are addressed the same. Bit 30 and bit 300, these are the same bit address. Up here, you typically don't use an output more than once, but here we're using this same number more than once. Once for the latch and once for the unlatch. So I push the start, it latches. I push the stop, it unlatches. Okay? Now to be aware here that if the stop is wired normally closed, that pushes a 1 into the data table. There'll be an indicator light on the input module. So this will get a 1. And so this will be reading false. This will be reading open as false. So when I push the close button, this will return to the state indicated, and then the bit will unlatch. And then here's the contact. We're using the bit to turn it off and on the light. So once again, here's the latch and unlatch. What do you prefer? Me personally, I like the parallel rung here to see that the memory is held and that my memory, my start and stop are all right there. On one rung, I can see that there's memory. This works right here. This is fine. The difference here is between, rung 3 and rung 4, which would be your latching and your unlatching. You could have 20 lines, 20 ladder logic rungs here. So it might be difficult to see if this was latched and if it was unlatched, if these two items were separated by quite a bit of additional programming in your program. Here it's all right there. So it's up to you. Some people use latch, some people use unlatch, and it just depends on the way the program looks. Timers. Most systems have a timer on it where something's timing on and off after you push a button and something starts, and then a few seconds later something else starts. And so back when timers first came out, there was pneumatic time delay relays, and this is what we used in 131. They used bellows, and then that moved, that changed, and they started using solid state time delay relays. There's no moving parts in here. They're very much more accurate, and they're pretty reliable. Okay, and then the PLCs kind of take the solid state operation and then it embeds it in the ladder logic. So now it's an instruction set that we can use. The advantages are it's easy to alter them. You usually just turn a little knob, and then that changes the amount of time that you want to use. On a solid state device, in a PLC, you just change the number. So if you want 1 second, you just change it to 2. So, and it's even more accurate than solid state devices where you turn the knob. You can increase or decrease without wiring. So even if you were using a solid state timer, you still have to get out wire cutters and wire that in. PLC, you just program it. And also the timers on the PLC are super accurate and repeatable because of the computer and the clock that's embedded in a computer. So when you look at a timer, you have a preset value. So this is the red represents the number of time periods the timer will time for. Okay, so basically you want to tell the timer, if you want to be a 2-second or 3 second or 4 second or half a second. This is dealing with that. The accumulated value. So that is as it is timing up. So let's say we have we want a 5-second timer, and then we activate it. We can watch on the screen as it times 1, 2, 3, 4, 5. This is watching it accumulate. Now the time base is kind of the accuracy of the timer. Do you need the timer to count by ones, 1 second, 2 second, 3 second, or do you need something, you know, much more accurate, like 0.01 seconds? So this would count very rapidly, 0.01, 0.02, 0.03. It would count in hundredths of a second. Or control logics count here in a thousandths of a second. They count very, very rapidly. It depends on your application and what is available. Okay, so the total time that you're going to get in a timer is going to be your time base times your preset. So let's say you had your time base of 1 second. You want the counter counting by ones. Okay, the timer's going to time by ones, and we put in a preset value of 5. So it's going to count 1 second 5 times for a total time of 5 seconds. If you had a time base of 0.01 and you wanted 5 seconds, you would have to put in a preset of 500. So it would count 01, 02, 03, 04, 05, etc. very rapidly 500 times, and that would you multiply those together and you get 5 seconds. Okay, so that's how you calculate your total time. It's your time base times preset. The SLC 500s that we're using, I think we're going to be using 0.01 time base. So you'll be multiplying the preset by 100 to get the appropriate value that you want. So timer and counters are addressed using T4, okay, up to T40, T41, T42, all the way up to T4255. Have a total of 256 timers. The contacts associated with this are the EN, which is the instantaneous. This represents the instantaneous contact on a timer. The done, that represents when the timer has timed out and reached the 5 seconds, for example. And then the TT is the timer timing bit, and this is true whenever the timer is timing. So in this case, it would start at 0, and if you activate the timer, this would be on for 5 seconds, and then it would stop. Okay. Here's a timer example video kind of showing you the EN, the DN, and the TT as it relates to a pneumatic timer. So the type of timers are TONs. So when you go to the instruction set and you see down here timer counter, so far we've been using the user and the bit. Those are where the rungs and the parallels and the XIOs, XICs, OTEs and stuff are. The timer counter is going to have my timers. So the first one is a TON. It's an on delay, and it is going to time the base interval when the instruction is true. On delay timing relay. So this is showing you a pneumatic timer, and on here you have instantaneous contacts on a timer, normally open and normally closed. So a PLC simulates that we do have instantaneous contacts, and remember that is called the enable bit. So it would be T4, let's say 0.en. That would be the contacts for this. The way that that would work is if I energize the timer, this is equivalent to giving voltage to a pneumatic timer. Okay, anytime that this timer has voltage here, the instantaneous contacts right here would close, because this is T40EN, the enable bit, and this is timer T40. So this timer has a time base of 1 and a preset of 400, so it's going to count for 400 seconds. Remember, after 400 seconds, this is still true. Oops, that stays true until the rung goes false. Let's take a look at some more. On delay timing relay. So we have our normally open time closed and our normally closed time open contacts. Okay, these are going to be simulated with the done, the .dn bit. So when the timer times out, it will get done. So here we go. We have once again a T40, and here's my done bit. So I close this, and the timer starts timing, and it times for 400 seconds. The total time, as long as this is true, remember the EN bit is true. But the DN bit is not true until the preset hits the accumulation hits the preset. So 1, 2, 3, 4, all the way up to 398, 399. When it finally hits 400, this closes and becomes true. So the done bit represents the time contacts. The timer timing bit is set to 1 whenever it is increasing. So in this case, this is true. So obviously, because the rung is true to the timer, the enable bit is on. That's the instantaneous contact. But this is accumulating. And so as this accumulates 50, 51, all the way up to 398, 399, 400, while this is timing up, this timer timing bit is true. But then once this hits to 400, this timer timing bit goes false. The done bit becomes true at 400, but the timer timing bit is now done being true. And that's a little bit different for you. So the timer timing is new, and it can be very useful. It is similar to the instantaneous contact being in series with a normally closed timed open. So let's think about this. If we brought power to a pneumatic timer, this instantaneous contact becomes true. This is true because it's normally closed, and so the light comes on. True, 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 light's on. The timer times, let's say 5 seconds, and then this opens. So this is still true because it's instantaneous. This is false, and the light goes off. So the timer timing can be very useful. It's on while the timer is timing, and that's different from a pneumatic relay. A retentive timer, the operation of an RTO, timer on, is very similar to the TON, except that it retains the value. So if you bring the rung true, it starts timing. If you make the rung false, it keeps the value that it's accumulated so far. Now with a pneumatic timer, you make the rung false, it just kind of resets, and then you have to start again. A retentive keeps your timer, and therefore it needs a reset instruction that has the same address as the timer instruction. So now this is the second time today where I've said we need to address things with the same address, even though we said earlier don't address things with the same address. We now have, if you're using latching, OTL and OTU, you're going to use the same address. And if you're using these timers here, you're going to address the timer with the address, and you're going to address the reset instruction with the same address. So these are a couple of times when you would use the same address. RTO, it's a retentive on delay, and so it counts time-based intervals when it's true, and it requires a reset. So the RES instruction is right here, and the RTO instruction would be right there under the timer and counter. The timer off, it is one that starts true, just like a pneumatic timer. So if you make the rung true, it kind of resets, and then when you make the rung false, then it starts timing. And this one does not need a reset. TOFs do not need a reset. TONs do not need a reset. It's just those RTOs, the retentive timers, are the timers that need resets. So my off delay timer, it had instantaneous contacts that behaved just like a normal relay, but we had our normally open timed open, normally closed timed closed contacts that we learned about for pneumatic timer. And so the way that this would work, once again, is if this rung becomes true at any time, well then the EN bit is going to be on, if you need to use the EN bit in your ladder somewhere. But if you make this true, the preset and accumulation are equal, and therefore the done bit becomes true. Okay, so it starts done. It doesn't time out and then close. In this case, this would close. When I released and opened up this contact right here, then this would start timing, and when it got to 400, it would then return this to the normal state, and the done bit, it would open. Okay, so it just works in reverse. Very, very similar to the way that the off delay timers worked in 131 for pneumatic timer. Here's our time symbol contacts for an on delay. So we had normally open time closed, and if you want to use a normally open time closed, then you have to take an XIC and assign it to a done bit. So think about that. An XIC assigned to a done bit. That is going to be represented by an open contact, and then that open contact assigned to a done bit. And so we have a timer that's like 5 seconds. After 5 seconds, that done bit will become true. So that examine close, that open contact will kind of close, and it will be seen as being true. And if you want an XIO assigned to a done bit for the normally closed time close contact. The off delay timers, here's the cheat sheet here. If you want a normal open time to open contact, you want to use an XIC contact to a done. And if you want a normally closed time, you use an XIO contact to a done. We'll be studying these in the lab to be sure that you understand how these work compared to the pneumatic timers that you learned on. Here's a timing example video to show solid state timing and some things like that. Counters. So counters keep track of parts going past a given point. And so in the past, they've had maybe actuating levers or something like this that would advance a counter, or you would have solid state counters that you saw that would add one number. And so it's just count control. And now the PLC takes count control and it makes it a lot easier, very similar to timers. It's just an instruction set that you can add to your program. And then you can use different bits to figure out if a counter is done counting, or if it's in the middle of counting, or if the counter is enabled. Here's your solid state counter example to see what's going on with the solid state devices. And now remember, these items here require resets. So you're gonna click this, and you'll see that the solid state devices are acted as retentive, and there's a separate reset button in them. So PLC counters can count up or down, okay, and they're retentive. If you stop the program and then you kill the power, then pull it back up, the value in the counter will remain the same. And that's the same for a retentive timer. If for some reason the power goes off and it comes back on, it's going to remember how long we've been timing, okay? So it will need a separate reset. The counting sequence is when the limit switch comes true, the counter value goes up. And then when it goes low, nothing happens. If it goes high again, that means somebody's pushed it, the counter goes to 2. Then it goes low. Comes high again, goes to 3, etc. It will accumulate until, or will increment until the cumulative value is reached, at which point the done bit will come true. You can keep accumulating. If this was a value of 4, you can keep going 4, 5, 6, 7, way past number 4. It's not going to change what's happening with the done bit. The done bit would be, if this was a 4 counter, it would be anything 4 or greater. The countdown decrements. So basically, if this prox comes true, it goes negative. It would count. So if this was like a counter that was at 10, it would go 9, 8, 7, 6, 5 until it met the preset, and then the done bit would come on. So it's a down counter. So counter up increments the accumulated value at each false to true. Here is my up counter right here. It's under timer counter again, and it's going to need a reset. It will have to be addressed. The reset will have to be addressed with the same address. Counters are C5. You'll learn that counters are C5. The counter down, it decrements. This counter down is right here. We are going to learn that there's up-down counters, where you take a counter and you address it the same. Once again, this is the next time when you would address a counter as a counter up, and then you would address the same counter as a counter down, and then they work together. The counter up would cause it to come up, and then the counter down would cause it to go down. So that's kind of a special case of where you would address the counters with the same address. But other than that, whenever you use a TON or TOF or RTO, or typically a CTU or CTD, they have their own unique address. Do not double address. The reset is going to be what double addresses, and that will be for the counters and the retentive, because these are all retentive. The RTO, the CTU, and the CTD are all retentive, so they need to reset with the same address. And resets accumulate available and stays a bit for the counter. That's what the reset does. Here's the instructions. Here's the counter enablement. So for some reason there's a switch over here and this counter is true. If this rung is true at any time, the enable comes on. Not that useful of a bit, but you never know when you might want to use it. The counter done bit. In this case, we have counter C5. I said counters start with C. Timers started with T4. Counters are C5. This is the first counter, 0. So every time this came true, 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 this would acclimate 1, 2, 3, 4, etc. When this accumulation reaches the preset of 10, then the done bit changes states, and this would then become true. Overflow, that means that we've reached the maximum value of the counter, and we'll see later it's over 32,000 counts. So the preset can be up here to 30,767. And the reset instruction resets it back to 0. And once again, it is addressed C50 with the same number, the same address C50 here. And those are some of the only times that you would want to use an address more than once. The down counter, here's the enable bit. So if for some reason the rung here is true, then this is going to be true. Counter done bit, once again, when the counter is satisfied, the preset and accumulation are the same. It will become done and this will close. Underflow, that means that the counter has went negative, not -0, negative 32,767. And then this also needs its own reset. Okay, so in this case, this is preset of 10, and if I make it, it would go 9, 8, 7, 6. This one counts down. Okay, here's my counters. You can count up or count down all the way to negative 32,768. If you go to negative 32,769, the overflow bit, the underflow bit will come on. If you go to above 32,767 up to 768, the overflow bit will go on. Here's a summary of the counter bits. That's my overflow when you exceed it. My done bit is when the accumulation in the preset, the accumulation becomes greater than the preset. Notice it says greater once again. So if my preset is 5, if I want a 5 counter, and I push 0, 1, 2, 3, 4, nothing happens. When I get to 5, the done bit comes on. When I go to 6, 7, 8, 9, 10, the done bit remains on because it's greater. Once you reset it, it then goes low again. The up counter enable bit, that's an instantaneous contact for the up counter. The enable bit is the instantaneous contact for a down counter. And then the underflow is if for some reason you down count and you go way low, lower than this, then you'll get the underflow bit to come on. Here's an example of doing some counters that you want to follow along. So there's a quiz for this unit and then a lab.